This is the first video for the material in Chapter 1 that covers sampling techniques and the sampling distribution of point estimators. The topics that we're going to cover include sampling from a population. When we select a sample, we will concern ourselves with two different types of populations that we can sample from: a finite population or an infinite population. And we will define what it means to sample with and without replacement. We will also talk about point estimation. Point estimation is a form of statistical inference. Basically, what we're doing is pulling a sample from a population and then trying to learn about the population by calculating a point estimate of the corresponding population parameter. Like we might want to learn, for example, about the population mean by pulling a sample and calculating the sample mean. Since every time we pull a sample, we're likely to get a different sample, we'll get a different point estimator of the population parameter with each sample. That implies that sample statistics or sample point estimators, such as X bar or P bar, the sample proportion, are themselves going to be random variables. So we're going to concern ourselves with the sampling distribution of these random variables, which are point estimators. This is going to be necessary in order to make probability statements or attach certainty to our point estimates or conduct hypothesis tests on population parameters using our point estimates. So we'll talk about how these sample statistics that we calculate are actually distributed as random variables. And a key to making statements about the shape of the distribution of sample statistics like X bar or P bar often relies on what's called the central limit theorem. So as a general rule, bigger samples are preferred to smaller samples because they allow us to state that the distribution of X bar and P bar are normal and bell-shaped if the sample size is large enough, even if the population that we're pulling the data from to calculate X bar and P bar are not normally distributed. So first, sampling from a finite population. Finite populations are defined by lists. So basically a list, or what sometimes is called a frame, can just be hypothetical. You don't have to literally make the list, but if you can conceptually build a list and then sample from it, then you're sampling from a finite population. So there are some obvious examples here. One would be a membership roster, or you could think of like undergraduates at Loyola University. You could make a list of all the undergraduates at Loyola University and then randomly sample from that list. I wouldn't want to enumerate all the credit card numbers for even one bank, let alone all banks, but at least conceptually, you could list them all and put them in a frame. And therefore, credit card account numbers would be an example of a finite population if we were to sample from those, etc. So the big concept here in terms of sampling from a finite population is what your textbook calls simple random sampling. And what that means is that we're going to fix our sample size at n. Oftentimes we'll fix our sample size at n, and then we'll see what happens when we repeat our sampling at size n a large number of times. But here we're fixing our sample size at m, and obviously n is smaller than capital M, which is the population size. And what we need to do for simple random sampling is make sure that every single possible sample of size n is as likely as any other sample of size n to be selected. And if that's the case, we have simple random sampling. What we're trying to avoid is some systematic way of sampling that introduces a bias into our point estimates. So let me give you an example of this. Suppose that we're looking at the student body at Loyola and we're interested in knowing the average age. Well, if I walked into an EC 220 class and surveyed everybody's age and I took an average, I would likely be committing a sample selection bias. And the reason is that most of the students in EC 220 are sophomores. So they're probably a little bit younger than the average Loyola student, since they're younger than both juniors and seniors on average. and I would not have collected a sample that is representative of the broader Loyola student body. So what we're trying to do here is make sure that we get a sample that's broadly representative of the population that we're interested in studying. The only other thing I'll say about this issue right now is that in economics and business, often we just have the data that we have. And even if we know that there's a sample selection bias problem, we may still have to use the data. And rather than adjusting the data, we have to adjust the techniques that we use. So there are statistical techniques that adjust estimates and account for the bias, but they're pretty advanced and they're well beyond the scope of this course. So in this course, we will just assume consistently that we're able to achieve simple random sampling when we deal with these types of cross-sectional data. So there's two ways of sampling. You can either sample with or without replacement from a finite population. If we sample with replacement, basically every time we sample another element, we're putting back all the previous elements that we sampled. So for example, if I pull a card from a deck of 52 cards at random, right, and I want to pull a second card, before I pull the second card, I put the first card back in the deck, probably shuffle it again, then pull at random the second card, etc. So there would be 52 ways of pulling the first card, 52 ways of pulling the second card, etc., according to our counting rule for multi-step experiments. Now, if I sample without replacement, then that's more like playing poker, where I pull one card out and I don't return it. I pull a second card out and I don't return it all the way until I get 5 cards. There are 52 ways of pulling the first card. There are 51 ways of pulling the second card. You know, there are 50 ways of pulling the third card, etc. And there are combinatoric rules for permutations and combinations apply. So a lot of times we'll use computers in order to help us achieve random sampling. Computers are very good with pseudo-random number generators. I'll show you an example of one of those later in a demonstration that comes in this presentation about halfway through. So when I sample from an infinite population, it's a little bit different. With an infinite population, you're talking about a process that's ongoing. And that kind of implies, just in the word ongoing, that we're dealing with something that's occurring over time, or what we often call time series data. So time series data is a little bit tricky compared to cross-sectional data. And the type of sampling that we're going to think of is just a little bit different. We don't have to get too hung up on the nuances here. But what I would like you to know is that time series statistics often requires a little bit of extra attention to these types of sampling issues, and when random sampling is violated, you know, sort of correcting for it appropriately. So some examples of ongoing processes or time series data where we would be sampling from an infinite population or an ongoing process where there's really no natural upper limit to the number of units that can be generated and observations that can be seen, would be parts that are coming off a manufacturing line, transactions at a bank, the telephone calls that arrive at a tech support desk, customers entering a store. Certainly most macroeconomic time series fit this definition of an infinite population. If you're talking about sampling, you know, quarterly GDP or quarterly GDP growth, inflation figures or price indexes, these are all really best thought of as ongoing processes and time series processes where we're sampling from an infinite population. In the case of an infinite population, the textbook makes a distinction between simple random sampling and random sampling, and the textbook authors say that random sampling is basically what we use in this case, the case of an infinite population, and for valid statistical inferences, they suggest the following. First, that each element that's selected into the sample comes from the same population, whatever population it is that we're interested in. Fair enough, that's easy. And then also that each element is selected independently of all the other elements that are selected. So just to give you an example, if you were looking at unemployment figures and it was an ongoing process and you had some type of a rule for selecting your sample which caused you to collect all of your sample elements from the same quarter of the year, you may end up with biased results because of seasonality. That would sort of be one example that would show you why you'd want to make sure that every single element that you included in your data set was sort of independent of all the other elements that you collected, and that you're not following some type of a careful rule to collect these observations, that they're as random as they can possibly be. So point estimation then is a form of statistical inference. And in point estimation, what we do again is we use the data from a sample in order to learn something about the population. So typically there will be a population parameter, and then there will be some sample point estimate that's our best guess of the population parameter. And the population parameter is fixed. It's whatever value it is. We might not know it. Mostly in this chapter, we assume that we do know it, but in most practical applications, we don't know everything we want to know about the population, which is why we're doing the statistics in the first place. But we know that there's some parameter out there. We want to get a good estimate of what it's equal to, and that's some fixed value. That's not a random variable. But when we pull a sample and we calculate a point estimate from the sample, which is our best guess at the population parameter, every time we pull a different sample, we're going to get a slightly different answer, which implies that our point estimate is in fact a random variable. And we really want to be concerned with the sampling distribution of this random variable, which is a point estimator, and we want to be able to understand the distribution of those point estimators so that we can add sort of confidence statements to say how confident we are about our point estimate, or we can do hypothesis testing about the population parameter using our sample data. That's where we're headed with this. So as just a couple of examples, X bar would be a sample point estimator of mu, the population mean. Now, the population mean is whatever it is. It's not a random variable. That's fixed, but we're trying to learn about it perhaps by pulling a sample. Every time we pull a sample, we would get a slightly different answer for X bar. Therefore, X bar is a random variable. This one is a random variable, even though it's our best guess of this one, which is not a random variable. So mu not a random variable, but X bar, the point estimator, is a random variable. We're going to learn about its sampling distribution. Same thing for S. A sample estimate of the population standard deviation. Right? Population standard deviation, it is what it is. It's not a random variable. But every time we pull a different sample, we'll estimate a slightly different value for S. Therefore, S is a random variable. Okay? We might want to know about its sampling distribution. Same thing for P bar, our sample estimate of a population proportion. That's a point estimator. It's a random variable. It's our best estimator of the population proportion, P, the true population proportion that shares some characteristic. But P is not a random variable, but P bar is its estimator. So first let's talk about the sampling distribution of X bar. The sampling distribution of X bar is the probability distribution of all possible values of the sample mean X bar. So again, I'm going to show you this in a minute, but you can think of it like this. We're going to fix the sample size, and just for the sake of argument, let's say that we fix the sample size at 30. We're going to go out into the population, we're going to pull 30 individuals out of the population, or 30 observations, and we're going to calculate an average, X bar. And we're going to put them all back. We're going to do it again. And we're going to put them all back, and we're going to do it again. We're going to keep doing this over and over and over again. And every time we do it, we get a slightly different answer for X bar. And we map out a frequency distribution of all the different values that we get for X bar. And that frequency distribution is the sampling distribution of X bar. And we want to know, well, what can we say about this sampling distribution? Well, what we can say about the sampling distribution depends on a number of factors. One thing that it depends on is actually the distribution of the population. Okay, it depends on that. It also depends on whether or not we know the standard deviation of the population. Okay, and it also depends on the sample size. So there are three things kind of going on here. We're going to cover each one individually. And so first of all, what I'm going to tell you is that in this chapter, I'm going to assume that we know the population standard deviation. We know it. Now, in many practical applications, we won't know it. and we'll have to estimate it from the same sample of data that we use to estimate x bar. When that happens, we will need a distribution other than the normal distribution. We'll need a distribution called the t-distribution, which we have not introduced yet, but we will. Okay, so for right now, we're going to assume that we know about the population. Just for the sake of argument, chapter is very pedagogical in that sense. It also depends, as I said, on the distribution of the population. If the distribution of the population that we're pulling our data from in order to calculate x bar, if that population is normally distributed, then I can say that x bar, the distribution of x bar, is also normally distributed. Okay, but if that's not the case, it's going to depend on the sample size, and that's when we get to the central limit theorem in a few slides. So I'm going to save a further discussion for then. Other things that we can say about the sampling distribution of x bar then, we can also say that the expected value of x bar is equal to the true parameter mean. So again, let's say that the average age at Loyola for undergraduate students is 23 years old. I go out and I truly randomly sample 30 Loyola students, and I calculate an average age of 22.8. I'm close, but I'm not right on, but I'm close, right? And then I go and I sample again, and maybe this time I get an estimate of 23.9. Right now I've overshot the true age by a little bit. Okay, but on average, if I keep doing this exercise where I put students back, I sample 30, I put them back, I sample 30, every time I'm calculating their age, I'm going to be hitting all around that target, mu. Sometimes on the left of it, sometimes on the right of it, sometimes real close, sometimes a little bit, a little bit farther away, but more often I'll be close. And every now and then I might hit it right on, but very rarely. Okay, but I'm going to be there at the right spot on average. Right, that's what it means for the estimator x bar, the sample mean, to be an unbiased estimator of the true population parameter, the population mean. Unbiasedness is a very important property in a point estimator. It's not the only important property, but it's one of the most important properties. Okay. So we're going to adopt the following notation, not just for x bar, but just in general. When we talk about the standard deviation of the point estimator, we're going to put the little point estimator down on the standard deviation as a subscript. So this is the standard error, or the standard deviation of x bar, what's called more generally the standard error of the estimate. We're estimating x bar, so sometimes it's called the standard error of the estimate. This is not to be confused with the standard deviation of the population. Okay? That's what we've already talked about. That's what we're assuming in this chapter we know. Practically, in practical applications, more often than not, we'll have to estimate that too. And that's what will lead to the t-distribution. But for now, I'm assuming we know that. Lowercase n, you already know, is the sample size. Capital N is equal to the population size. Okay? So in addition to thinking about whether or not the sampling distribution of R is bell-shaped, and in addition to thinking about where it's centered, the fact that it's unbiased, we're also interested in knowing, well, what's the standard error of the estimate? What's the standard deviation of the sampling distribution of the mean? And here are two formulas that you can use to calculate it. They're actually very similar to each other. We'll start with the one that looks a little bit easier on the right. That's for an infinite population. So what I'm talking about here is the size of n. I'm talking about the size of the population. If I have an infinite population, or n is really, really large, then I can calculate the standard deviation of the sampling distribution of the mean simply by taking the standard deviation of the population and dividing it by the square root of the sample size. Very easy formula to use. And that's going to be the standard error of the estimate that I'm going to be interested in using, for example, if I'm calculating z-scores that are related to x bar, right, to the point estimator. Over here, we've got a formula that is the same as the one on the right, except it tacks on this finite population correction factor on the front. Okay, and what we're really concerned with here is what happens to n. Okay, n is the population size. So holding lowercase n, the sample size, fixed, you can see that as n grows, both it's not super obvious, but if you know L'Hopital's rule, it's pretty obvious. So you can take this limit and see that as as n goes up, basically all the stuff that's under the square roots here, it goes to 1, and you end up with an equivalency between these two formulas. So if n is really, really large, then the difference, and I'm talking about capital N here, the size of the population. If the population is really large, holding the sample size fixed, then these two estimates of the standard error of the estimate are going to give pretty much the same answer. So when should you use the finite sample correction factor? Well, your textbook recommends, we can go with this, and as good as any other rule, that when your sample size as a percentage of your population size is smaller than 5%. So if your sample is less than 5% of the population, right, then a finite population can be treated as an infinite population. Go ahead and use the simpler formula. Typically that's what we're going to use, but not in every case. Okay. So n minus n over n minus 1, the square root of that is called the finite population correction factor again. Okay. And again, we call the standard deviation of the sampling distribution of the mean just the standard error of the estimate, or the standard error of the mean for short. So all of those terms can be used interchangeably. Here's the central limit theorem. Now, like I said, if we're pulling our data from a population that's normally distributed, then the sampling distribution of our mean, which will always be centered on the true value of the mean, we know that, and we know how to calculate the standard error, but it will also become bell-shaped or normal, a normal distribution, or a normal distribution will be a good approximation. Well, it will be normally distributed if we're pulling our data from a population that's normally distributed. But even if we're not, if we have a big enough sample size, the central limit theorem will let us treat the sampling distribution of the mean as though it's normally distributed. That's the power of the central limit theorem. So in selecting random samples of size n from a population, the sampling distribution of the sample mean x bar can be treated as though it's approximately normal as long as the sample size is large enough. Well, when is the sample size large enough to use the central limit theorem? As a general rule of thumb, most people will tell you that the sample size of 30 or greater is large enough to treat the sampling distribution of the mean as normally distributed, even if the population you're pulling the data from is not normally distributed. So if you have a distribution for the population that's skewed more, you might need a little bit of a larger sample size, like maybe 50. So in the population from which we are selecting a random sample does not have a normal distribution. Again, if it has a normal distribution, no problem. No matter what the sample size is, you're going to have a normal sampling distribution for the mean. But if the population isn't normally distributed, then you need a large sample. And you can apply the central limit theorem, and it will tell us that the sampling distribution of the mean can be treated as though it's normally distributed. Now again, all of this assumes that you know the standard deviation of the population. You don't have to estimate it. If we have to estimate it, we'll be talking about a t-distribution. We'll cover that in the next chapter. But I like to make that point at least 2 or 3 times here. So here's the sampling distribution of x bar. When the population has a normal distribution, I've already said this, but we'll cover it for completeness again here on the slide. The sampling distribution of x bar is normally distributed for any sample size. Okay, you don't have to worry about that if the population is normally distributed. Don't worry about the sample size. In most applications, the sampling distribution of x bar can be approximated as a normal distribution, even if the population isn't normally distributed, as long as the sample size is 30 or more. That's the power of the central limit theorem. So in cases where the population is highly skewed or outliers are present, samples of size 50 or more may be needed to apply the central limit theorem. But typically you can get it by with a sample of size 30. So the sampling distribution of x bar can be used to provide probability information about how close the sample mean is to the population mean. Okay, we're going to do that. We're going to do that next here. So I'm going to switch. I actually want to demonstrate for you. I want to demonstrate this idea of a sampling distribution for you. Okay, so what we're going to do now in this video is we're going to take a look at at a little experiment where I'm going to show you how we can sample from a uniform distribution. And when we sample from that uniform distribution, ultimately we can calculate an average. We'll see that that average, or that sample mean, it looks really like an unbiased estimator of the true mean from the uniform distribution, and that when we plot the histogram, or the distribution of these different sampling means, when I repeat the experiment a number of times, that it becomes symmetric and bell-shaped, right? Depending on the sample size. Even though I'm pulling the data from a uniform distribution, calculating the mean and doing that over and over again, as long as my sample size is large enough and the central limit theorem kicks in, the distribution of those means looks like it's bell-shaped and normal. That's what I want to show you. So don't worry about the code and stuff here. This is a program called Python, which I use a lot, and I put this little demonstration together in Python. All you need to know is that what I'm going to do right now is I'm going to pull 1,000 different random observations from a uniform distribution. I'm going to plot them for you below the actual theoretical distribution that I'm drawing the data from, and I'm going to calculate for you the mean. Okay, and that mean we can compare to the true theoretical mean, which is equal to 15. So let's just talk about unbiasedness for a minute. So let me pull 1,000 different observations from a uniform distribution, which runs from 0 out to 30 with a mean that's obviously equal to 15. So take a look at this number down here. You can see that I ran this experiment, and I came up with a sample mean of 15.27, which isn't equal to 15. I've overshot a little bit, right? That answer is a little bit larger than 15, and it's based on this sample of data that you can see graphed below. So if I run this again, it's going to pull a different sample and calculate a different mean. Let's do that and see what it looks like. So I run this, and okay, I did it again. Now you can see this time 15.42. I've overshot the mean a little bit. You can see that, once again, and you can see that the sample that I drew doesn't look exactly like the parent population, but it seems to be a reasonable estimate of it. The mean is certainly close to the true mean of 15 here. So let's try it again. We do this any number of times that we desire. You can see this time it's 15.14. It's a little bit closer. Do it again. This time it's 14.79. I've undershot it a little bit. I'm always going to undershoot it a little bit. I'm going to overshoot it a little bit. More often than not, I'm going to be closer than I'm going to be, really, really far away. But I've got sort of an unbiased estimate of the population mean 15 from my sample means. When I keep repeating my sampling process over and over and over again, I'm undershooting it sometimes, I'm overshooting it other times. It's a random variable, this sample mean, but on average it seems to do a pretty good job estimating the value of 15, which is the true theoretical mean of the uniform distribution that I'm sampling from. What I'm going to do in the next step is I'm going to take 1,000 replications of an experiment. Set that here, my number of replications. What I'm going to do is I'm going to go to this distribution, and I'm going to do this 10,000 different times. I'm going to go and I'm going to take a sample out of size 5, 10,000 different times. I'm going to calculate 10,000 different values for x bar, for the mean. And then I'm going to build a frequency distribution of those values of x bar for you, so we can see whether or not the distribution of the sample mean really looks like it's a symmetric bell-shaped curve. So the first time I did this, you can see that I set my sample size equal to 5. I went out and I collected 10,000 different different samples of size 5, calculated the mean for each one, and plotted a histogram for them. And what you can see from my histogram is it doesn't look that bell-shaped, right? I mean, there are a bunch of points over here to the left, and it kind of jumps up at 10, and it kind of flattens out, and there's a big peak here that's to the right of 15. 15 we know is the actual theoretical mean. Then it kind of drops off really sharply. It really doesn't look that symmetric or bell-shaped with a sample size of 5. But let me change the sample size. I'll increase it. And I'm going to jump to a sample size right up to 30, okay? So if I jump to a sample size of 30 and I rerun this code, it's going to go through and it's going to take 10,000 samples of size 30 this time. Not 5, but 30. And it's going to calculate the sample mean. It's going to plot this histogram. The 30 again, we'll try it at 30. There you go. There at size 30, you can see a nice symmetric distribution again. Okay, so it looks very bell-shaped, starting to approximate a normal distribution. That's sort of a demonstration for you of the power of the central limit theorem. You know, we started out with a sample of size 5. We got something that didn't look symmetric at all. When we approach 30 as our sample size, it starts to look nice and bell-shaped and symmetric. You know, right up until we get to, like, you know, maybe 50 or so, and the thing starts to really look like it's being well approximated by a normal distribution. So there's this a demonstration of the central limit theorem for you. Coming back to our slides, let's briefly then talk about the sampling distribution of P bar. So coming back to our slideshow, we could talk about the proportion. Let's say that we're talking about the proportion of U.S. citizens who have a bachelor's degree. So those over 25 who have a bachelor's degree. Let's say that that's what we're interested in estimating. So we're interested in then not necessarily going out and interviewing everybody in the United States who's 25 or older. We might do that every 10 years in a census, but in between census years it's too expensive to do that. So instead what we do is we go out and we get a random sample of people and we calculate P bar from that random sample. And P bar is going to be an unbiased estimate of the true population proportion of individuals age 25 and older who have a bachelor's degree. So the way that we state that is we state it by saying that the expected value of P bar is equal to the true population proportion of people who have a bachelor's degree or more, right? In other words, P bar is an unbiased estimate of P. Now I'm going to assume for now that I actually have that census data and I know what the true population proportion is. More often than not, we won't know that, and we'll have to estimate it from the sample data as well. But for now, I'm assuming I know everything about the population of interest. So again, we need to concern ourselves with the standard error of the estimate, in this case, the standard error of the sample proportion. And that is going to be calculated by taking P, the true population proportion of individuals that have a bachelor or more, age 25 and older, times 1 minus that proportion divided by the sample size. And that gives me a good estimate of the standard error of the estimate, or the standard deviation of the sampling distribution of the sample proportion. Now again, what we're concerned with here is the size of n, right? How big is the population? And can we assume that we have an infinite population? If we have an infinite population or something close to it, then these two estimates are going to give us pretty much the same answer, and we'll be able to ignore the finite population correction factor that we've tagged onto the front of this first formula. It's the same finite population correction factor that we used when we talked about the sample mean. So the same types of considerations apply here. More often than not, we'll be able to use the right-hand formula because we will have a population which is large relative to the size of the sample that we've drawn. So we refer to this now as the standard error of the proportion, or more generally, again, the standard error of the estimate. And we have this finite population correction factor one more time that we use if we have a very small population relative to the sample size that we've drawn. So the sampling distribution, one thing I want to say about the sampling distribution of P bar is that in general, it's binomially distributed, right? I mean, n can be considered fixed, right? Sample size is really considered fixed here. We're not going to change it, right, from one sample to the next. So the probability then of getting x successes out of n is basically like a binomial experiment where what's changing is the number of successes and the probability of getting that number of successes, and that's related to the proportion, right? P bar is the average number of successes, or the number of successes out of, it's really the number of successes out of these n trials when we went and selected n individuals to make up our sample. So the binomial distribution is quite important here. But if n gets larger and larger and larger, the binomial distribution, it becomes less skewed, and it becomes more symmetric, and it looks like the normal distribution. In fact, we say that the normal distribution is the limiting distribution of the binomial distribution. At large sample sizes, they become indistinguishable from each other. When can you use the normal distribution as a stand-in for the binomial distribution when dealing with sample proportions? Well, whenever n times p is greater than or equal to 5, and n times 1 minus p is greater than or equal to 5. Okay, we'll see an application of that. So the sampling distribution of p bar can be used to provide probability information about how close the sample proportion is to the sample mean. And we're going to take a look at an application of both the sampling distribution of x bar and p bar in the second video lecture for chapter 7, which is uploaded at the same time that this video is uploaded.